video, we will start learning how to find limits. Now, we are going to do that today two different ways. We are going to do it graphically, and we are going to do it analytically. Alright? So obviously, your heading would be finding limits or solving limits. Either way is fine. Graphically and analytically. Okay? And we're actually going to be looking at lessons 3.2 and 3.3, so please make note of that in your notes. And like I always say, I would encourage you to write down today's date so that you have a record of that in your notes. The reason we're looking at two different lessons is lesson 3.2 can easily be covered in one day plus a little more, so we're doing half of lesson 3.3. Alright, so finding limits graphically and analytically, lessons 3.2 and 3.3, and be sure and include today's date. Now, let's start off by looking at a familiar function. Okay, we've studied rational functions before. We know what a rational function is. So let's start off by looking at a familiar function. Here it is. Alright, please copy that in your notes. F of x equals x cubed minus 1 over x minus 1. Alright, please copy that in your notes. Now, here is the graph of the above function. If you were to graph this, you would get this. Let's talk about this graph and how it relates to a function, okay? Now, by the way, if you want to make note in your notes, this graph is on page 210, okay? And remember, the method we're starting off with is solving limits graphically, so you might want to make notes in your notes. Make a note in your notes that this picture does come from page 210, okay? Alright, now, please watch this carefully. Whenever you're asked to find a limit, you have to be given a specific number that the limit is approaching. Okay, now I promise you, I'll explain that in just a couple minutes. But whenever you're asked to find a limit, you are given a number that the limit is approaching. Now in this problem here, I want you to look at this graph as it approaches positive 1, okay? So in other words, we're going to find the limit. Write this down, please. We're going to find the limit as x approaches 1. Got it? So we start over here in the graph and we trace the graph, and we're going to see what happens as we approach what number? 1. So we start from the left. Now watch carefully. And I trace the graph. Now you don't have to do it this meticulously. I'm just trying to prove a point. And I get closer and closer and closer to 1. Okay, here's 1 right here. Here's 1 right here. If I drew an imaginary boundary line going through 1. So as I get closer and closer to 1, I hit this point here. Now whenever you're evaluating a limit by using a graph, listen students, you must do so from both directions. I would make note of that in your notes. Whenever you're evaluating a limit by using a graph, you must approach the number from both directions. So I approached it from the left. Now I'm going to approach it from the right. So I come down and I come to this point here. Okay? So as my x values changed and they got closer and closer to 1 from both sides, the y values also changed. For example, when I was here, I was there on the y-axis, then I was here, I was there on the y, here on the x. As I moved closer and closer, as my x values changed and I got closer and closer to 1 from both sides, this limit ended up being what number? 3. So as x approached 1, I came from the left and I came from the right. And you say, Mr. Earhart, where'd you get the number 1 from? I gave that to you. You will be given that in a problem. So as the limit approached 1, or as x approached 1, the limit equals what number? 3. That's pretty simple. Now obviously they get much more difficult than this, especially when we start solving them analytically. But today, all the problems are very simple, graphically and analytically. Alright, so as x approaches 1 from the left and the right, the limit is 3. The limit is 3. Now, having said that, I feel like there's a really important note I need you to write down, okay? Because students get confused all the time. They forget to look at the value on the y-axis. It happens to me, and I've done this for a long time. So here's the note I think you should write down. This is a key note. When finding a limit by using a graph, the y value, not the x value, is always going to be the answer. If there's an answer now, I probably shouldn't have put this. I mean, you can copy it down if you want to. It's up to you. Because you might say, oh, there's not an answer sometimes. Well, we'll get into some of those before the notes are over, okay? But sometimes there's not an answer. But right now, if there's an answer, when you are finding a limit or evaluating a limit or solving a limit by using a graph, the y value, not the x value, is always going to be the answer if there is an answer, okay? So what we did here for this problem, we said as x approaches 1 from both sides, what is the y value? Well, it's 3, okay? It's 3. Now, moving on, still referring back to the previous problem, let me show you what limit notation looks like. It's very important that you see this, okay? So referring back to the last problem, which was this right here. Okay, there we go. Sorry, students. Okay, now, referring back to this problem here, I need to show you what limit notation looks like, okay? Please take really good notes on this, okay? Now look. The last problem, written as a limit, would look like this. Watch carefully. You could say the limit of f of x as x approaches 1 equals 3. Please write that down. Now, if you wrote it like that, understand off to the side, you would have to tell me what f of x equals. That's why I cut and pasted this right here. I mean, without this right here, without this is nothing. You're just saying the limit of a function, f of x. Well, guys, I've got to know what the function is, okay? So, one way to write the last problem that we did is like this. The limit of f of x as x approaches 1 is 3. Do you see how to read that? The limit of f of x as x approaches 1 equals 3. Now, this is pretty decently abnormal. You'll see them like that sometimes, but not very often, because usually if they're going to write out the function like this, then they'll just pick this up and put it right here like this. This is more common here, but either way, both of these are fine. Here you would just say the limit of x cubed minus 1 over x minus 1 as x approaches 1 equals 3. Same thing. Here I put f of x because the function is f of x equals x cubed minus 1 over x minus 1, or you can just write out the actual part of the function that you're evaluating, and this is more normal right here. The limit of x cubed minus 1 over x minus 1 as x approaches 1 equals 3. There you go. It's that simple. This is called limit notation, and this is how you would write the problem. So if I would have given you this problem here, like that, you would have looked at the graph right here, saw how it was approaching from the left, how it was approaching from the right, and you would have saw that your answer was 3. That's how you solve a limit graphically, okay? Now, as I mentioned earlier, sometimes limits don't exist. Got it? Let's take just a couple of minutes and look at some examples like this, okay? Please take some really good notes, alright? Now, if you want to make note in your notes, this graph is from page 212, okay? Now, what if I asked you to find the limit of the absolute value of x over x as x approaches 0? Well, okay, no problem. So you're given this problem here. And then you look at the graph of it. So here we go. So I come from the left like I'm supposed to, tracing the graph. And I come to this point here. Remember, this is my boundary. I'm trying to find the limit as x approaches 0. 0's right here. So I'm going to put a vertical line. That's the line I'm trying to approach. Okay, so I'm trying to approach this line. So I approach the line, and I come to this point here. I approach the line from the left, from the right, and I come to this point here. Well, you can't have two. I mean, I know in some equations you can have two answers. Not when you're solving a limit. A limit means you're looking for the one number that the function is approaching as your x values change. So your x values change going from left to right until they got to 0. Your x values change going from right to left until you got to 0. And when you got to 0, your y value was -1. But your y value is also what? +1. So when you approach it from the left, then you got one answer. When you approach it from the right, you got another answer. Now, we will not get to this in this video. However, there are, I'm forgetting the actual notation. I wish I could remember. There are some limits where they will say, approach the number, and they'll put a positive sign. I think it's here. That means approach it from the right only, or a negative sign. That means approach it from the left only. But we're not getting into that right now. Right now we're doing basic limits, which is you approach the limit from both directions. You cannot have two answers for a limit. Thus, the answer to this is no answer. Does not exist. Undefined. Whatever. Okay. There is no answer. Do you see why? We're getting out two different y values when we approach it from the left and the right. Let's look at another one like this. Here's another example. Now, if you want to make note, this is also on page 212. If I'm going too fast, you know what to do. I would rather go too fast and have the supervising teacher pause the video than go too slow and have you be bored. Okay, so if I'm going too fast, just pause the video now. We're going to find the limit of 1 over x squared as x approaches 0. The limit of 1 over x squared as x approaches 0. So I'm going to go ahead and put a vertical line here going through 0. That's my line that I'm looking for. Okay. Now, as I go left to right, look what's happening, students. Please look. As I get closer and closer to 0, the graph continues to go up, 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 up. Think about it. You know that. I mean, let's see if I can slide this down a little bit. Let's get rid of this. Let's go like this. Pull this down. Here's my y-axis continuing upward. Look, as I get closer and closer and closer to 0, it's increasing without bound. In other words, let's say it's 4, 5, 6, 7, 8, 9. Right here, as I got close to 0, the y value is 9. But then as it goes up, it's getting closer to 10. And as this curve gets closer and closer to this vertical line, it continues, the y value continues to get higher and higher and higher. It never, if you will, it never bottoms out. It never comes to a number. I mean, as you think about it, guys, as this graph right here gets closer and closer to that vertical line, it's going to continue. As it gets closer, it's going to go higher and higher. There's no set y value. You can't say that as this approaches 0, the y value was 100. Because if you go a little closer to 0, then it's going to be 110. And if you go a little closer to 0, it's going to be, or maybe negative, it's going to be maybe negative 120. Or excuse me, it wouldn't be negative, sorry, but it would be 120 or 130. And it's going to continue to increase. The closer you get to 0, it's never going to settle or bottom out on one y value. So the answer to this would be no solution, no answer, cannot be done. There is no limit in this problem. Okay, I hope that's making sense. Back it up and watch again if you need to, guys, but think about it. As you get closer to 0, which is the number you're supposed to approach, the y values are going to shoot up and get higher and higher. They're never going to settle on an exact number. All right, now let me get a drink here. Finishing things up, we have looked at evaluating limits by using graphs. Now let's look at evaluating limits analytically, okay? We will do 3 of these types of problems. 3. And they're actually pretty simple. It's almost an embarrassment to your intelligence. They're pretty simple, but we're starting basic and moving on, okay? Now, here are the 3 problems we're going to look at, alright? So first of all, I want us to evaluate this limit analytically, not using a graph. Now, if you want to use a graph, that's one, we're going to do that, but also you must learn how to solve these analytically. And by the way, analytically is much easier than graphing. Okay, we want to find the limit of this expression as x is approaching 3. So you know what you do. Are you ready for this really difficult math? Everywhere there's an x, you put in 3. And I just messed it up, didn't I? That takes skills. 2 times 3 minus 5. 1. So, the limit of 2x minus 5 of x as x approaches 3 is 1. Really, Mr. Harry? Yeah, it's that easy. Look, if you were to graph this linear equation, you would get 0, negative 5. 1, negative 2. 2, negative 1. No, it'd be negative 3. 1, negative 3. If you put a 2 in, you would get out negative 1. And if you put a 3 in, you would get out 1. So there's the linear graph right there. There's the linear graph. You don't have to write this down if you don't want to. I'm just showing you. Here's 1, 2, 3. So as the limit approaches 3, as x approaches 3, here's 3. So draw your vertical line right through 3. There's the point right there. Here's 1 over here. As you approach it from the left and get closer and closer to this vertical line, there's the point. As you approach it from the right, there's the point, and that point is where on the y-axis? 1. That ordered pair is 3, comma 1. So as the graph approached 3, the limit was 1. Isn't that easy? Now they don't all work out this easily, and there are some that you cannot solve analytically. You've got to look at the graph and do some table of values and stuff like that. But there are plenty that you can solve this way, okay? Alright. So here we go. Let's try another one pretty simple. If I ask you to find the limit of an expression as x approaches a certain number, just substitute that number in. Alright? And we're pretty much good to go. Alright, let's try this one here. Now, that's a negative 2 in case you can't quite see that as x approaches negative 2. So the limit of 3x minus 2 as x approaches negative 2. So where the x is, I'm going to substitute negative 2. Well, that gives me negative 6 minus 2, which gives me negative 8. Now, I'm not going to draw the linear graph again like I did in the last problem, but if you did, you would see the point negative 2. The point negative 2, negative 8 right here would fall on the linear equation, okay? So, as x approaches negative 2, the limit of 3x minus 2 equals negative 8. There we go. So we did a couple easy ones there to kind of get your feet wet and to help you understand what we're doing. Now let's look at one more problem that's a little more difficult, and let's see if you guys can't figure this out, okay? This will be interesting. Now, I want you to find the limit of this expression here as x is approaching 0. Alright? Now, if you use the method I just taught you, everywhere there's an x, here and here, you're going to substitute 0. So let's try that and see what happens, okay? So I have 0 over 0 plus 1, and then negative 1. Well, the numerator is 0. That's obvious. Let's simplify the denominator, alright? 0 plus 1 is 1. So now I have the square root of 1 and then minus 1. Well, let's simplify the denominator even more. The square root of 1 is 1. 1 minus 1 is 0. So you should have been taught in the past that 0 over 0, if your denominator is 0, you get undefined. okay? Or you get infinity if it's 0 over 0. Nonetheless, whatever you want to call this, the answer is no solution, no answer, or so you think. Please listen to me carefully. Sometimes when you evaluate a limit analytically, you'll get out an actual number. Sometimes it won't work. But here's what I don't want you to miss. Are you ready? Don't miss this. Just because analytically it didn't work doesn't mean there's no answer. There still could be an answer. You just might need a graph to help you, or a table of values, or there are some other methods we'll learn later that you can do to this. But my point is this: just because it fails analytically doesn't mean there's not a solution. So let's take a look at the graph now of this, and I want to show you what happens. Let's stop and review. So when I do this analytically, I'm getting out no answer, undefined, no solution, whatever. Now look at the graph. Okay, now if you want to make a note in your notes, we're on page 211. I'm going to make this a little bigger so we have some room to work with here, okay? Alright, there we go. Now, look at the graph carefully. As this graph approached, okay, I'm trying to find the limit as x approaches 0, right? So draw your vertical line right here, going through x is at 0. Now what that does is it shows you the boundary you're trying to approach. Now from the left, start tracing the graph until you get to this point here. Now from the right, start tracing the graph, and you get to this point here. Now you're saying, Mr. Earhart, if you look at that graph, if you look at that point, it's undefined. Yes, it is, you're right. But when we're solving for limits, we're asking what is x equal, listen to me, as you approach 0, okay? Not as x equals 0. Now you say, hold on, back here, Mr. Earhart, you told us to actually put 3 in for x. Yes, because sometimes that works, because sometimes the graph is defined at that number. So why not do it the easy, quick way first? Why not? Well, the answer is we should. But when analytically it doesn't work, don't just, as the old saying goes, throw the baby out with the bathwater. Don't just assume there's no answer. You've got to check it with a graph or other methods we'll learn later. So, look, this limit does exist. As I approach from the left, I get this number. As I approach from the right, I get this number. That's at 2. The x value is 2. So the limit of x over the square root of x plus 1 minus 1 as x approaches 0 is 2. You couldn't do it analytically, but graphically you can. Okay? Alright, that's a quick little, not intro, but a little start to studying limits. I hope this video has been a help to you. If you have any questions,